Starting off here in the morning, we have Rob Connor from Purdue University talking about the effects of pack-out corrosion in steel bridge members. So let's welcome Rob.
Not that tall. So good morning, everybody. Got to be energy, right? It's early in the morning. Normally right now I'd be teaching an undergrad steel design class. And so I have to be very energetic teaching the undergrads to keep them awake, which I don't do quite well. So hopefully I can do okay today. So I just want to give an update on a pooled fund project. Some of the partner states are actually in the room looking at the effects of pack-out corrosion. You all know what that is and have to deal with it all the time. The focus of the project is to, it looks really bad, right? You get these really terrible looking steel members that look like one of my grad students who is from Spain. He now works for Michael Baker. He had a great phrase for it. You know, the edge, how it kind of just rolls along the edges like in the photos there. He calls it the lasagna noodle pattern, right? And so you see that in the pack out and everything. The question is it all that bad? And so we had done some other work on internal redundancy, which is now in an AASHTO guide specification, and kind of thought, well, we did a lot of research looking at those members and kind of felt, well, what hasn't really been looked at in a similar way? And this is one of those topics, right? So it looks bad. There's research on, holes in beams and things like that. But what about built-up members with pack-out? So the project has some pretty basic objectives focused on pack-out, right? Is it an issue, right? But one of the things we like to do at Purdue, and I think we've been good at, is turning the research into practice, whether it's AASHTO specs, AISC specs, ACI, whatever it's going to be, so that then there's some implementation associated with it. So that's really the goal, right, is if there's a way to codify, to give owners a way to evaluate the effects of pack-out. And then also on the need for repairs. In other words, it looks bad, but do I really need to do anything, right? Do I need to strengthen the member? And hopefully, if we have some time left at the end to kind of give guidance on maybe some best practices. And then, of course, have examples, right? So if you had this, here's what you do. And I definitely want to acknowledge our partner states. The study is still active. If anybody thought this was interesting and wanted to continue to support the project, that would be great, because this is what we call in the research industry as a COVID project. Right, so this is one that started kind of right at the beginning of COVID, and we kept graduate students funded and things like that. And so financially, a lot of universities dealt with some significant burdens because of COVID, just trying to keep people employed like everybody did. But it hit the research group pretty hard. So I'm going to focus on the testing that we've done, how we came up with some of the members, some fatigue testing. That'll be the real focus, and some strength tests, and then just kind of give you a little teaser on some of the compression member work that we've been doing, and then some conclusions. Now, one of the things that's critical when you go into tension, right, if you're looking at fatigue or fracture, and fracture meaning kind of strength, all those little nicks and gouges from corrosion and all that have to be in the member. I can't simulate that. Right? We want to have the real damage. So that means we need real members with real corrosion. Well, when we were doing our internal redundancy work, we obtained some members from Minnesota DOT from a bridge called the Winona Bridge. And it's been a challenge to obtain members with corrosion coming out of service that then get, programmed properly to be able to be used. But we were able to use some members from the Winona Bridge, I'll show you, and then some members we had at our bridge center at the S-Bright Center. So again, the members came from Winona. It was in service for 60 plus years, maybe 70 years, and it was a big river crossing up there in Minnesota. So here's some photos of the members, and we've gotten a lot of mileage out of these. We did internal redundancy tests from previous work, and then the ones that were more damaged were very useful for this project, right? So again, about 75 years of service or so when the bridge came out of service. So these were tension lower chords, so they've already seen fatigue cycles, probably low stress range, right? Because in service we see low stresses. Now the challenge with these is, although they're great and they have pack out, they're truss members. And in fatigue or in strength, it is difficult to test things in pure axial tension. The loads go huge very quickly. Flexure is a much more attractive way to do fatigue testing or strength tests. But they're the typical built-up member you would see. These were rolled channels with cover plates, right? So that's where our pack-out corrosion ended up happening, was where we had the cover plates. So we converted these then to flexural members. Right? So we take the truss, the cord, we separated it into two halves. And then we treat those halves as flanges with a constant moment region, so the flange is effectively in uniform tension over a given length. And so we split the cord, right, cut the batten material out of it, and then now we have these members. Now you'll notice they're cleaned up, and that had to do with the lead paint. The fabricators couldn't work with the lead paint, but we told them to take care not to remove the pack out. Now, if you've ever tried to remove pack out, it's hard to do. So blasting, through a wheel abrader doesn't really take it out. It's like rock, right? It doesn't come out too easy. So we split the members, and we end up having 4 separate components. We then added on a flange, onto this, our new flange, added on a web that is then bolted on and allows us to reuse the upper portion of a plate girder, right? So basically we took these, split them, and built plate girders, right? Then we can load them in flexure, which is much easier to do to get stress ranges we want at more modest loads using servo-controlled equipment. Then we bolt that all up, right? And this top piece we can reuse, and then the bottom piece we just change it out, right? So we create this nice eye-shaped member. So these were pretty good size, right? Decent flexural members. They're big and difficult to, you're not going to pick it up by hand or anything like that. Then we take that member and we document the damage a lot. And we did this by hand. We tried to do some of the photogrammetry, and it worked okay, but it just wasn't working out as good as we would have liked. So we took the time to go and lay out grids and so forth and measure all that damage. And you take all that information, and then you can map it out, right? And get a feel for where most of your damage is. And that becomes useful to put into like finite element analysis, right? You can map all those surfaces in there. But the point is, there was a lot of damage, and there was a lot of section loss, right? So these are severely damaged components. In terms of loading for fatigue, we have a couple of large setups at the lab at Bone Laboratory to allow us to run multiple fatigue tests at a time. So we are running twin fatigue tests side by side to try to go as fast as we could to collect the data. And some tests were done in strength for compression members, but for fatigue, these setups work out really nice. And so we have an 8-foot constant moment region or zero shear, right? And so that gives us a nice uniform stress range over a significant length of rivets and where the damage is. And then we have a shear span portion also where we have a fair amount of damage and stress range, but also a good amount of shear. So here's the 30,000 foot results. I'm not going to get into the details and show you each specimen. Now, bridges operate at low stresses, right? In reality, we talk about the categories. Our goal, fatigue categories, our goal was not to define a fatigue category, right? So we're not running at 20 KSI and these high stress ranges that we typically do. Because in real bridges, when you instrument them, you operate around 3. Maybe you'll get a 5 KSI once in a while. Our goal was to try to say, in real operational circumstances, does the pack out hurt you, right? Because that's what you're dealing with, bridges in real service. Now, rivets are typically classified for first cracking as Category D, so we ran just over the threshold for Category D. Now, while that's good, it's also painful because you start looking at the cycle counts that you need. They get very high very quickly at low stress ranges when you're running just above threshold. Now, if you're familiar with the AASHTO fatigue curves, there's also what's called the design curve, the curve when you open up AASHTO you see. That's the lower bound curve, and that's associated with a 97.5% roughly probability of survival. In other words, if I ran a fatigue test to the AASHTO curve, it shouldn't crack. So I don't want to stop my test there, right? Because there's only a 2.5% chance something should have cracked. So we run past that. You can run to the mean or the upper bound. We chose to run to upper bound. In other words, there's a 97.5% probability that it should have cracked, right? Now, again, they're scatter and riveted members usually do better than D, but that's where the data fall out. So that means we have to run these specimens out up above 15 million cycles. We chose to run even higher, up to 20 million cycles. Now, remember, these already had 75 years of life on them, right, in service. Now, what happened? Nothing. Right? There was no cracking that you could point at and say, yep, see, the pack out killed our fatigue resistance. Now, there were a couple cracks that appeared at other rivet holes, like in the sides and things where there was no real pack out or anything, and it should crack, right? It's well beyond the lower bound. But in the regions of the pack out, there was no negative impact of the pack out. So, Category D, which what you could use for evaluation, still seems to be reasonable when you have significant pack out. But that wasn't good enough for us. We said, okay, well, we've done all that. let's jack up the stress range. So we took specimens and ran it up to 12.5. Why 12.5? Well, category C is a threshold of 10. Riveted members for evaluation in the MBE were allowed to use category C. So we said, well, let's go above category C and see what happens. And, it's hard to dial in perfectly. So, the number is 12.5 to 13, lower bound of 2.25 million up to 7 million. We ran these up pretty high in terms of life. We didn't take them all to upper bound because they already had a lot of damage on them already. And nothing happened again. The only cracking we saw was on a side plate. If you remember, they were channels, and there were some rivets for batten plates on the side vertical leg of the channel. A couple of those started to crack. So that was good news, right? Now you can combine all that data into effective stress range calculations, and this is the big takeaway. Is if you look at the data and you look at your category C or category D with the dashed line, either it's a run out, nothing happened, or, and again, these are all to the upper bound lives, or there was a crack, but it had nothing to do with the pack out. It was just a crack at a rivet hole. So why the good behavior? Well, if you've taken apart pack out, now, and I'm just talking members with good old pack out, right? Not the stuff where there's like, holes you can put your hand through the web or something like that. But when you separate those surfaces, they're actually very smooth. If you split open pack out surfaces. And what we think is happening, and we're looking at this analytically, which is hard to do, but if you don't create damage from the distortion, or you don't create these crazy pits because the surface is pretty smooth, then it becomes a stress concentration factor that really drives fatigue. Well, if the distortion, that gives you a stress concentration, right? If that distortion doesn't exceed the stress concentration associated with a plate with a hole in it, basically stress concentration of 3, then you're not going to see worse behavior. Does that kind of make sense, right? The distortion amplifies the local stresses. You get bending, you get this stuff going on. But if you don't exceed anything worse than what the hole is, just from the pack out, then it kind of makes sense that you wouldn't see a reduction in fatigue strength. So how would you implement this? Well, right now, here's what we're thinking. That, again, we're not trying to define a category, so we wouldn't tell you it's category C or D. We would use threshold numbers. Like, if your stress range in reality is kept below this value, then it's as good as it was before for category D. And again, in real bridges, you're not operating at 15 KSI or something like that, right? So this would be one where, well, if you were concerned you were running high, you could put a strain gauge on it, show you were actually a lot lower. And maybe we'll consider category C. We would still have infinite life concepts, right? If you have pack out. And again, I'm not talking about when something's completely destroyed. So the challenge then is going to be, what is that limit, right? We had about 1 inch to 1.5 inches of distortion. And you can correlate the amount of distortion or pack out to how much section loss. And so that's the guidance we're trying to craft now, right? How do you implement this? If you had a 1/2 inch of pack out, does it matter if you have 1 inch of pack out and plate size versus rivet spacing? So that's all being done right now. But the good news is, if you had a member with pack out, it doesn't appear that the pack out itself is going to kill you in terms of fatigue or have it looks bad, right? But it doesn't seem to be that big of an issue. Now, that's fatigue. The other side then is strength, right? What does this do to us in terms of strength? We didn't anticipate a big reduction in strength based on the work we did on internal redundancy. And that work was when you would fracture a single cover plate, right? So you have 2 or 3 cover plates and you fracture one. What does that do to the strength of the member? Well, in that work where there was no damage, there was really no effect. So the thought was, well, I wonder if that's still going to work here. So analytically, even with the distortion in the finite element models, it showed that there wasn't going to be an effect. And again, the internal redundancy work suggested that as well, but we had to confirm it. So we took the girders that had the equivalent 30 million cycles on them or whatever, right? Took them and put them in another fixture and did strength tests where we would take them up and try to see what the ultimate strength would be. So this takes a lot more load. We have to switch our fixtures. And the numbers I want to call your attention to are in the undamaged condition, all right? So if we just said, what was the girder the day it was new? What's its MY? What's its MP? Right? These are the kind of KIP loads we'd be looking at, significant loads to get to MY and MP. And so, again, these already had damage on them. So, what's the summary of this? Well, we tested these two, and if you look at the KIP numbers and where we're yielding, As it turns out, take a look at that red text. With a cut cover plate, we loaded them up, nothing really happened. So we kind of like to say, well, what's the worst thing that could happen? Well, the cover plate that has the distortion in it fails. Somehow it fractures, it corrodes away, whatever. So we cut it. You still get to MY of the undamaged cross-section. Now you might think, well, why is that? It's not there. And the reason is in built-up members, there's a neat behavior. It isn't a single plate, right? It's not one component. It's a whole bunch of components stitched together. And when you sever one component, the load comes out, goes through the fasteners, is into the others. The takeaway is you don't get widespread yielding. The yielding stays very, very focused, right? And so because of that, the material that hasn't yielded around the material that's yielding, gives you constraint. In other words, it gives you a benefit in terms of strength. So the member hardly deflects. The stiffness really isn't any different. You will never perceive deflection if you have a broken component, but you can get to the full strength. And so that's also good news, right? In fact, one of the specimens basically got to MP, except we had some issues with some bracing that started to fail for lateral torsional buckling. So the strength part seems also consistent. So what we think would be the recommendations that are in the internal redundancy specification, we could still utilize those, right? Okay, so they look really bad, and it turns out it doesn't seem to be that big of an issue. Now, this is the kind of pack out, we're talking like where this is 1 inch to 1.25 inches, right? So it is significant. So in the big picture, our goal is to put some simplified methods to assess pack out, right? If there is an impact on strength, right, maybe we'd have a lower fee factor or something like that just to be conservative. No change in stiffness, so we would give guidance on that, and fatigue as well. And then this idea of mitigation, right? When should I go in and do something? Now, this data would say, well, it can get pretty bad before you need to do anything, but how much do you want to let it continue, right? I mean, it's still going to continue to corrode. So that's language we're trying to figure out right now, and then turn this into AASHTO specifications. And then that's all in tension, right? That's tension flanges. However, for compression, we're also doing work on sub-members, small members that have really bad corrosion and holes in them and things like that. And when it comes to compression, I don't need all the little nicks and gouges, or I shouldn't say nicks and gouges, but the pits from corrosion that could hurt me in fatigue, right? In compression, I don't need that. And so we came up with ways to, simulate the pack out, okay? So where we would distort plates, just tightening bolts together, then putting in mild fasteners. We machined plates away and then added distortion. And that allowed us to dial in different levels of distortion in compression, different levels of section loss, right? And that's really great for calibrating finite element models. As it turns out, as you can imagine, there's not a big effect, right? And it's kind of obvious, right? If you have, 2 cover plates and you lose one, the overall impact of that cover plate on the cross-sectional properties usually is somewhat small. And if it's only portions of it that are damaged, what we're finding is like a real easy way to address this is you just say, well, anything outside of the rivet, maybe, I don't have that material. I just pretend that material is gone. For tension, that's very reasonable. For compression, our only concern, and this is what we're looking at, is, well, yeah, but this little buckle could want to get bigger, and maybe that gives me some odd behavior. So maybe I have pack out on this side, not on this side. How does that hurt me? So that's what we're looking at right now. You do get some funny effects with this. In fact, in compression members, I was talking yesterday, if you have compression members and they pack out, you can actually see an increase in buckling capacity. Completely counterintuitive, but the member's getting bigger, right? And it's a D squared, remember your calcs on section modulus, moments of inertia, right? And so even though the member is losing section, it pushes out, you're chasing, right? Area is a linear effect where the D squared, right? That becomes a nonlinear effect. And so you actually see slight increases in capacity. So I'm not encouraging to spray salt water on members to get strength, right? But it's one of those funny things, right? And so it kind of ends up making sense. So anyway, we're looking at the compression side as well. Parametric studies on that are underway right now. And we do a lot of work with Python scripting where you can set, vary the rivet spacing like this, and it automates things quite effectively for us. So it's a real interesting project. I think it's going to have some good impact for our industry. And hopefully the next time maybe I am presenting this somewhere, in the next year we'll have some basic code and commentary we'll be running by AASHTO. So with that, I'm open to try to answer any questions if I have time left. Just for those of you who, we have a lot of our SBRITE partner states here. If you haven't ever visited, come visit sometime. That's our bridge center where we do a lot of our inspection training and so forth, large-scale specimens and so forth for the SBRITE Center. So nice little playground we get to have for our bridge research, inspection, and training.
Thanks, Rob, for the presentation. Very interesting. So you said that one of the hopeful results is going to be some guidance to the bridge owners on when they should consider doing something to their, when they see it, when should they think about it? Because I know now people think, oh, we better do something. And what you're saying is maybe not right.
Maybe not, at least from a strength or fatigue point of view. And that's, and not to be academic, right? I know there's other reasons to fix stuff, right? Because, I might look at it and say, well, I don't think it's going to hurt you, but it's going to continue, right? And so our guidance would be more, at this point, you better do something because you're going to lose strength soon, or there could be a fatigue effect soon. That would be independent of, well, yeah, but the corrosion is going to take off. I can say some of the people who are involved with the project, the states who've done mitigation, kind of feel sometimes they've accelerated the problem by taking out the pack out and basically creating cups for water, things like that, because some of the sealants don't work super great and things. Right now, I'm kind of a proponent of, if you're at that point where you have a long way to go before you get to damage. So you have a ½ an inch of pack out, and this work would say, oh, you can get 1.5 inches. I don't know if I'd be too quick to do anything, because it's probably going to take you 30 years to get that next inch, right? So if you could, and that I don't, I'm not an expert in the coatings of different ways to treat it, but yeah, but I think we would be able to say you probably got another 10 or 15 years before it gets to that point. Yeah. Okay, thank you.